Okay, this is a tutorial on how to use the Simplex algorithm to solve a linear programming problem. We'll be looking at the matrix solution as well as the tableau version and comparing it to our graphical solution here. Our original problem is a maximization problem. The first thing that we want to do is put this into standard form by getting rid of these inequality constraints and making them equality constraints. Also, we want to add some slack variables here. So, for our first iteration, we want to identify what our initial basis is. This involves our initial basic feasible solutions, which are x3, x4, and x5. We want to then find our z value that relates to these basic variables, and you can perform this matrix operation to get 0, or you can also see on the right-hand side of our table that it is 0. Now, we want to check to make sure that this is optimal or not. And to do so, we find our reduced costs right here, and we can see that x2 has the least reduced cost. Therefore, we want to allow x2 to enter into the basis. Now, if we allow x2 to enter the basis, we want to make sure that the problem would still be bounded. To check for this, we analyze the a2 hat vector by performing this matrix operation right here, and our a2 vector is going to be this right here. And then since at least one of these elements in our column vector is positive, we can assume that our problem is still bounded. So now we want to find that once we allow x2 to enter, which variable will be leaving the basis. And we've determined this by looking at our ratio test. As you can see here, we divide our right-hand side of our current basic solutions divided by our a2 vector here, and then we choose the minimum of these. And that shows us that x4 needs to leave the basis. Now we want to make x2 column look like the x4 column, and to do so you perform these elementary row operations. So now we're at this current solution, and we want to move on to our next one. So for iteration 2, we have a new basis here. As you can see, we also have a new cost vector. And now we have a new z value. It has improved, which is a good thing. However, we can see that this is not yet optimal. And we see that concerning that we have this negative value right here for x2 or x1, and we determine that x1 now needs to enter the basis. So similar to iteration 1, we confirm that it is still a bounded problem because we have at least one positive value here. Now, to determine which variable needs to leave the basis, we look at our ratio test here, and we can see by ignoring the negative values, we can see that x5 is going to be the x3 is going to be our leaving variable. So you can see here we want to highlight our least value for our ratio test, which corresponds to, and we want x1 to enter, and we want x1 to look like the x3 variable. So to do that, we want to perform these elementary row operations, and then we will look at the next iteration to determine if this is an optimal solution. Now we are at this point of our graph right here with our new basis and our new cost vectors. As you can see, our z value has in fact increased once again, which is a good thing. However, we are still not yet optimal because we have this negative value for our reduced cost, which correlates to our x4 column right here in our table. So now we want to also confirm that it is still bounded if we allowed x4 to enter the basis, which it is since we still have this positive value right here. Performing the ratio test and not looking at the negative values for our ratio test, we can see that x5 is going to be our leaving variable, and x4 will be entering it. So to make x4 look like our x5 vector column vector, we want to perform these elementary row operations. Now we can look at the next iteration to determine if we are optimal or not. As you can see here, through our procedures from our previous iterations, we are at this point right now. And looking at our graphical solution, this should show that we are optimal. Since our isocontour line is increasing this way, this would be the last point in which it would hit. Now we can confirm that this is optimal. Well, it's true that our z value has increased. Also, we have no more negative reduced costs, meaning that we are currently optimal. And this can be confirmed by looking at our row 0 and how we have no more negative values for our variables in our row 0. And we are now optimal.